Here are solutions to homework set number 4 for ECE 461 control systems. This homework set looks at Laplace transforms, basically review of signals and systems. The first problem is, suppose x and y are related by a transfer function. What is the differential equation that represents? Well, to find that, just cross multiply out the polynomials, and note that s means derivative, so s cubed is the third derivative of y, s squared second derivative, first derivative, just y, derivative of x and x. So this differential equation is the same thing as that transfer function, just another way of writing it. You can also use the prime notation. Prime means derivative. That's just easier to type, easier to write. Same thing. Part B. Suppose x is a sine wave. Solve for y. This is actually a phasor problem. This is true for all s. All I care about is what's the gain at s equals j3, the frequency of the input. In phasor notation, the input is 4 minus j5. The real part is cosine, minus j is sine. So in phasor form, here's the gain. Analyze at s equals j3 times the input at 3 radians per second gives you the output at 3 radians per second. That's a complex number where the real part represents cosine, minus j represents sine, and frequency stays the same. Part C. Suppose instead x is a step input. Now solve for y. In that case, take the Laplace transform of x, multiply by the gain, and that's the Laplace transform for y. It's a Laplace transform when it turns on at t equals 0. This is not in my table of Laplace transforms, but I can use partial fraction expansion. There's something over s, something over s plus 2, s plus 5, s plus 10. Do partial fractions, you get your numbers. And what that tells you is now take the inverse Laplace transform. Y of t is 0.3, minus 0.2, e to the minus 2t, minus 0.26, e to the minus 5t, plus 0.15, e to the minus 10t for time positive. So there's y of t. Problem 2. Suppose x and y are related by this transfer function. Use second-order approximations to determine the 2% settling time, percent overshoot, and steady-state output for step input. Here the dominant pole is the one closest to the origin, minus 1 plus minus j5. So this is actually a second-order system. The settling time is 4 over the real part. 4 over 1 is 4 seconds. The angle of the pole, here's the pole at minus 1 plus j5. Here's the angle. That's arctangent of the imaginary part of a real part. 5 over 1, well, minus the real part, is 78 degrees. Again, the angles for damping ratio is measured from the minus x-axis. Cosine of the angle is 0.19, so that's the damping ratio, 0.19. From the second order approximation sheets, if I know the damping ratio, I can find the overshoot. 0.196 damping ratio gives an overshoot of 53%. And the DC gain is just g of s at s equals 0, 0.128. So the step response should look like this. I've got 53% overshoot. The settling time is 4 seconds. And the DC gain is 0.128. If I check, I'll take the actual third order system and put that into MATLAB. Take the step response. Let's take time from 0 to 6 seconds. The settling time is 4 seconds, so let's go a little bit beyond the settling time. Calculate the step response using MATLAB and plot it. And here's what it looks like. Here's the step response from MATLAB. I also drew onto it the DC gain in red. That's your steady state gain. The overshoot is 53% more than DC. So there's my overshoot right here. And that pretty much matches up. It won't be exact. Second order approximations are exact for second order systems. This is really a third order system. So it'll be close, but a little bit off. Problem 3 is the Jeopardy question. Here's the step response. What's the system? Well, I know right away this is a first order system, pretty much. There's no oscillation, so I know it's something over A over S plus B. I need to pull two pieces of information off the graph. One of them is the DC gain. As S goes to 0, the DC gain is 2.95, about. The settling time. This is the transient. When is the transient within 2% of the steady state value? And ballpark, it's right around here. Hard to tell exactly. If I say about 80 milliseconds, that tells me the real part of the pole. The settling time is 4 over the real part of the pole, tells me the real part's at 50. So B is 50, pick A to make the DC gain 2.95, and there's your step response, or your transfer function. If you want, you can go into MATLAB and find the step response. It should look almost the same. Problem 4. If this is the step response, what's the transfer function? In this case, I know I have complex poles because it's oscillating. So that's roughly what the transfer function looks like. I need to pull three pieces of information off the graph. One of them is the DC gain. As S goes to 0, the DC gain is about 3.4. Second one is the settling time. That tells you A. The settling time is ballpark right around here, about 110 milliseconds. That tells you A is 36.4. Again, you're not going to get that to 7 decimal places. Ballpark, 110 milliseconds. Frequency of oscillation. Here's the minimum. There's 1 cycle, 2 cycles, 3 cycles in 82 milliseconds. So that's the frequency of oscillation in hertz. Anything English is wrong. Converting it to radians per second, it's 229 radians per second. So that's where your pole is. The real part's 36, complex is 228, plus its complex conjugate. The numerator is a fudge factor, whatever it takes to make the DC gain 3.4. So that is roughly G of S. And that is homework set number 4 for ECE 461.